Our universe, it operates on scales that are just kind of hard to wrap your head around. It's full of numbers so incredibly big or so mind-bogglingly small that just writing them down is a challenge. But what if I told you there's an elegant language, a system designed to tame these titans, a way to make the immense, well, manageable? Let's dive in. So, to really see what we're up against, let's start with a real-world question. How much information, how many bits of data, are packed into a single hour of high-resolution digital film? I mean, it's something we use every day, right? But the number itself, it's absolutely staggering. And there it is, 130 trillion. That's not just a number, it's a monster. Imagine trying to do any kind of math with that thing. It's clumsy, and you're just asking to make a mistake. Honestly, all those zeros are a complete nightmare to keep track of. But here's the good news. There is a much, much better way. For centuries, mathematicians and scientists have been sharpening a toolkit to deal with exactly these kinds of numbers. And today, we're going to build that toolkit for ourselves, piece by logical piece. Okay, our first tool in the box tackles multiplication, and it's really the foundation for everything else we're going to do. It's called the product rule of exponents, and it's this incredibly neat shortcut for what is, let's be honest, a very repetitive problem. Let's break down why this rule even exists. If you've got x to the power of 3 times x to the power of 4, you can just write it all out, right? That's 3x's multiplied by 4 more x's. So how many do you have altogether? Well, you can just count them. You got 7. And that simple act of counting just gave us the shortcut. Instead of writing everything out every single time, you can just add the exponents. 3 plus 4 gets you 7. So x cubed times x to the 4th is just x to the 7th. That's our first rule, and we figured it out just using pure logic. All right, so we have a rule for multiplication. The next logical step, of course, is its opposite, division. So how do we simplify things when we're dividing expressions with exponents? Again, let's look at it visually before we get to the rule itself. If you have y to the 9th divided by y to the 5th, you can write out all the factors. Now, for every y on the bottom, you can cancel one out on the top. In this case, 5 y's down here cancel out 5 of the 9 up there. So, what are we left with? We're left with 4 y's on top, or y to the 4th. The shortcut then is pretty simple. You just subtract the exponents. 9 minus 5 is 4. And that's our second tool, the quotient rule, and it comes directly from this idea of cancellation. Okay, so now let's push this new rule a little bit. Let's see if we can break it. What happens if the exponents are exactly the same? I mean, we know from basic math that any number divided by itself is just 1, but what does our fancy new rule say is going to happen? Let's look at this two ways. On the left, if we write it all out, we see that every single factor cancels out, leaving us with exactly 1. But on the right, if we apply our quotient rule, we get t to the power of 8 minus 8, which is t to the power of 0. You see where this is going, right? The logic here is just inescapable. If both of these methods are perfectly valid, then their answers have to be equal. And that means that anything to the power of 0 must be 1. We just discovered another fundamental rule of math, just by being consistent. Pretty cool. All right, time for the next logical puzzle. What if there are more factors on the bottom than on the top? Our rule says we should subtract, which means we're about to run into a negative exponent. What could that possibly mean? Let's do that side-by-side comparison again. Visually, the 3 h's up top cancel 3 from the bottom, leaving 2 h's down in the denominator. So the answer is 1 over h squared. But our quotient rule, it gives us h to the power of 3 minus 5, which is h to the power of negative 2. So this means that h to the negative 2 must be the exact same thing as 1 over h squared. And that gives us our next rule. A negative exponent just means take the reciprocal. It's not a negative number at all. It just means you're dealing with a fraction, usually a pretty small one. Okay, so, quick recap. We've covered multiplication, division, zero exponents, and negative exponents. There's just one more core tool we need for our kit. What happens when you raise a power to another power? You know the drill by now. Let's visualize it one last time. X squared to the power of 3 literally just means you have 3 groups of x squared all multiplied together. So that's 2x's times 2 more again. All told, that's 6 x's being multiplied together. And this simple little drawing gives us our final core rule. The fastest way to get there is to just multiply the exponents. 2 times 3 is 6. So when you raise a power to a power, you multiply. And with that,
Our basic toolkit is complete. We built it.
Now, remember that ridiculously large number from the beginning? It's time to go back. With these rules in our pocket, we can finally unlock a really powerful and, frankly, elegant system for handling these giant numbers. It's called scientific notation. So what exactly is scientific notation? Well, you can think of it like a universal shorthand. You just rewrite any number as a digit between 1 and 10 multiplied by 10 raised to some power. That power, that little exponent up there, that's the key. It holds all the information about the number's true scale.
The whole trick, the real magic here, is just counting the jumps of the decimal point. So for a big number like, say, 2.7 million, you move the decimal to the left until there's only one non-zero digit in front of it. In this case, that takes 6 jumps, so the power of 10 is 6.
And that's really all there is to it. It's a simple 3-step process. First, you move the decimal. Second, you count your jumps. And third, you write it down in that standard form. This elegant process can handle any number you can possibly throw at it, no matter how huge or how tiny.
And this is why it all matters. This isn't just a math trick. The distance to the Andromeda Galaxy is a 24 with 21 zeros after it. I mean, that's not just annoying to write. It's a barrier to actually doing anything with it. But 2.4 times 10 to the 22nd power? That's clean, it's precise, and you instantly get a sense of its scale. Same thing for tiny numbers, like the length of a red blood cell, where our old friend the negative exponent tells us just how small it really is. So think about what we just did. We started with this beast of a number, and using just pure logic, we built a complete set of simple rules to tame it. We've basically constructed the language that scientists use to measure and describe the entire universe. So the only question left is, now that you have these tools, what will you measure first? The universe is waiting.